Oh, in the previous video, we talked about error in the Hough line transform detector. Specifically, the error arises when the line cannot be accurately represented by pixels. So, because this line has some ambiguity as it was represented by pixels, then when we calculate the two collinear points, we actually don't get a perfect match. So we would actually get a line based on here that is actually slightly off. And the longer this line, the further away this line is away from the origin, the further away this line is, the greater the distance is. So if it gets here, then now you can, the line transform essentially will tell you that the line is there as opposed to here. So if you were to draw this in a graph, in a rho theta graph, then the curve may be off. So that is a problem. One of the ways that we resolve this is through clustering. So instead of looking for intersections, we would actually look at this section. So if there are anything that intersects in this section, then we would say that, you know, they're in the ballpark. So if there's an intersection here, then there must be a line here. So that's one way to resolve it. But the problem with this clustering is, well, if you were to recognize different lines in an image, what happens if my regions overlap? Then what does this overlapped region mean? You know, is there a line here or is there a line there? What does that mean? So this creates quite a problem for us. So one of the solutions that was proposed is to minimize this distance and minimize the distance between these two collinear points. So the way to do that is to pick the center of origin delicately. So in an image, actually I'll draw a bigger image. So in an image, we would pick the center of the image as the origin, and then we would recurse on each of the sections to try to minimize the distance between them. So let's draw an image to show what that looks like. So we have our image. So instead of having the center of origin here, then our max rho could be this much. That's our maximum rho. So then our lines distance could be, our collinear points can be here, or our collinear distance could be here, right? So if we have a distance like that, then the variation, the error, can be quite significant. So what we would do is we would have the center, we would have the origin in the center. So we would divide the image into a quadrant, and now we would have the center of origin here, and now the maximum rho is here, which is half of what it was before, right? So in the worst case, if you have a line that's something like this, then the maximum error is almost half of what it was before. So that is one way we can improve the situation by making the image that we're working with smaller. So, and the good thing about this is that you can, working on a smaller image, the theta, which is the angle of the image, is preserved. I'll show you what I mean. So if I have a line here, this line has this theta, right? But if we move the center of origin to, say, here, this line will still have the same theta. So in this way, we can use smaller origins, and this origin and this region is going to give me smaller error than using this origin. So in this way, I could use here, I can use this region, and then here, I can use this as my origin. And then once I do that, I combine the calculations together, and then that way I can greatly minimize the error of the lines. And that is one solution that we can use to divide and conquer the image into smaller sections, and then we find a clever way to combine these pieces together. And as we combine them, we will get a much lower rate than if we were to do them all in one big image.